Good afternoon, everyone. My name is Doctor Courtois. I'm a PhD candidate in the Laboratory of Electronics, Antenna and Telecommunication at the Université Côte d'Azur. And today I'm pleased to share with you some of my thesis work. The demand for intelligent and autonomous systems capable of sensing their environment is rapidly growing. Think about it. The reactivity required for drones, for spacecraft, this system must operate independently, often in harsh and constrained environments. Embedded vision systems, which combine vision sensors, dedicated hardware, and optimized algorithm, is a challenging task. While traditional AI offer impressive capabilities, their hardware often struggle to offer such a demanding condition. But a promising link emerged from biology. According to the scientific literature, the human brain uses only about 20 watts of powers, yet it controls the complexity of our body with remarkable capability, such as cerebral plasticity, multimodality, massive parallelism, sparse and event-based behavior, and even at low frequency. In this way, our brain outperforms any digital computer for equivalent tasks. And as an answer, neuromorphic systems are inspired by the brain's behavior, explore energy-efficient solutions that can operate where conventional systems struggle. In this work, I explore the limits and possibilities of bio-inspired approach for digital embedded event-based vision systems. This work was made possible thanks to two projects. First, the DeepSea project, which is a 3 years project funded by the ANR and coordinated by Benoit Miramond. And the second project is the Emergence PEPA AI project coordinated by the INRIA, CNRS, CEA. This project is a 6-year project funding at the national scale. For the agenda of the presentation, I will talk about the first little state of the art to set the boundaries of the event-based sensors, spiky neural networks, and neuromorphic architectures. We'll see after the metrics and the workflow that we've developed in order to test if spiky neural networks are truly energy efficient. And after we'll go forward to see a more complex use case with embedded event-based object detection. And at the end, we will see advanced network architectures exploration with event-based spacecraft pose estimation. And at the end, I will conclude and discuss about the perspective of this work before answering the jury questions. First, every event-based vision system needs event-based cameras. These sensors are inspired by the human retina. They are sensitive to brightness, and when there is a brightness variation, when this variation reaches a certain threshold, the camera sends an event which could be positive or negative, depending on the variation. Each event is encoded with a position on a pixel, X and Y, the temporal resolution, the T, and the polarity. These cameras are high resolution, high temporal resolution, high dynamic range. They have a low light cutoff, and they are independent in the pixel way, which means that unlike formal cameras, they didn't output images, but rather a stream of events. This stream of events need to be processed by neural networks, and to process this kind of this list of events is really hard for the training. So we can represent them in many ways. One of them is the 3G point cloud when we use the time, but this way is really computationally intensive, and in this work, there is many ways that exist, but in this work, we mainly use voxel grid representation, which works with a discretization of the time in order to, in time bins. Each time bins can be interpreted as an event frame where we put the events inside regarding their timestamps. And the aggregation of the timestamp of the event in these time bins can be either binary, but we can lose some information, but it's lightweight. But we also can just count the number of events in the time windows in order to have a sum event frame which have more information, but we have to deal with integers. For the neural part, Spiking neurons are neurons that are inspired by the functioning of neuron in the brain. Each model is a trade-off between computational efficiency and bioplausibility. For machine learning tasks and in this work, we will focus on the integrated end-fire and leaky integrated end-fire. These neurons accumulate weighted inputs into a membrane potential until a certain threshold is reached, triggering an output spike and resetting the potential. Leaky integrated end-fire also add a decay factor, which can allow the time interpretation and better control of the time. Since we work on digital hardware, the time is discretized into time steps, allowing to unroll the accumulation and decay over several time steps. However, this threshold mechanism is introduced non-differentiable functions that didn't allow to use direct backpropagation for training. But with this neuron, we can build spiking neural networks. And unless non-spiking neural networks that we will call formal neural networks in this presentation, these formal neural networks have a dense computation and in a synchronous way, so at a fixed frequency. But spiking neural networks, because of the spiking behavior of the neurons, have an asynchronous and event-driven processing of the information, which means that they process the information as it arrives. They use sparse computation, which means that all neurons are active at the same time, and we can compute the activity of this neuron by looking at the sum of the events over the number of neurons. They have a time dependency capacity with the membrane potential of the network, and this sparse behavior and this binary stream of events allow a reduction in the multiplication and accumulation operation in the network, which can lead to energy efficiency computation. But we need to, in order to use this kind of network, we need to fix the training issues and also to have dedicated hardware. For the training, we can use backpropagation only if we use a surrogate gradient, which means that we can use different functions for the forward pass and the backward pass. This offering the best result in terms of accuracy, but necessitates higher training efforts. But also, it can have some temporal issues when there is a lot of time step in spiking neural networks. And in 2018, NFC and colleagues released the backpropagation through time for SNN, which can unroll the network in the backward pass in order to keep the temporal dependency and internal states. This has some memory and computational costs, but have a really better gradient computation, and this is the best results with SNN actually, and that's why we are using it. Now that we can train the network, we can see which neuromorphic architecture we can deploy them. And neuromorphic architectures are architectures that have massively parallel distributed memory and event-driven computation. Then can be sorted in three categories: analog, mixed signal, and digital. While analog and mixed signal categories are really promising for their efficiency and biological realism, they suffer from issue in scaling and integration. So we will focus on digital architectures. Now there is a lot of companies that already sell this kind of chip, but this ASIC platform offer low energy computation, but they're often black box in terms of circuit and also in terms of energy measurement. So it's really less flexible for software and hardware co-design. Besides this, FPGA-based approach like split ModNef or Seneca consume more energy than ASIC solution, but can offer also more latency. But they offer circuit synthesization, practical testing, and also they are really flexible for hardware-software co-design. In this work, we use mainly splits, which is the spiking low-power event-based architecture developed in the laboratory by Edgar Lemaire and Nassim Abderrahman. This architecture is optimized for spiking neural network processing. It can target FPGA or ASIC and supports binary sparse and event-based processing. The core unit of split is the neural processing unit, which can compute events in address event representation regarding of the type of spike that we want to use, integrated fire or leak integrated fire. And the address event controller allow us to support sparse fully connected layers and sparse convolutional layers outputted in the buffer. In the version that we use here for this thesis, we use the first one of the first version of split, where one NPU can be attributed for one layers to deploy feed-forward networks, spiking feed-forward networks. Now we have seen all the steps to build embedded event-based vision with an event-based cameras, neuromorphic hardware, and spiking neural networks. But before going to deployment, we need to see how can we estimate the efficiency of our approach in terms of spiking neural networks, and also we need some tools for efficiently deploy and evaluate spiking neural networks on our hardware. For the operation content energy estimation metrics, before 2022, in the literature, many assumed that SNN can replace all the multiplication and accumulation by accumulation only, which leads in papers by the energy estimation of SNN being estimated with the energy of one addition multiplied by all the operation of the networks, resulting in the SNN being over like 100 times more energy efficient than formal networks. But this matrix is really simplified and often overlook memory access pattern, neuron addressing, memory potential issues, and decay factor and spiking routing. To overcome this matrix, to go a step further, we decide to build the hardware agnostic matrix with the total energy depending on the operation, addressing, and memory costs to have a more realistic for FNN and SNN comparison. For the addressing, we just look at the number of the energy for accumulation and multiplication accumulation operation. Which means that we can compute the energy for accumulation with the number of the energy for an addition times the number of accumulations, and the energy of multiplication accumulations by the energy of an addition and a multiplication times all the multiplication addition needed. For the memory, we need to see the energy of the read and write access to this memory, and multiply it by all the memory access, which are for the inputs, the parameters, and the output. And for spiking neural networks, there is also the update of the potential that had an overhead for this. But the key parameters of this matrix are the energy for the addition, multiplication, and the read and write access. But these values are really kept secret by companies. But in 2021, Juppy and colleagues released some value about different bitwise for integer and float additioner and multiplier, but also for different memory access size. And in order to fit any memory access size we needed for a network, we just did a linear approximation for this in order to have the value of our energy for the read and write. To test our energy, our energy metrics, we tried 3 datasets. The first one is a CIFAR-10 dataset, which is an image classification. The second one is the Google Speech Command dataset, which is audio signal recognition. The third one is the NCARS, which is event-based classification of images. And for each of these datasets, we trained 2 networks, one FNN and one SNN, in order to do the comparison. For the VGG, we built the VGG 16 with 4 time steps for the CIFAR-10 use case. We built the 4-layer CNN on 2 time step for GSC, tiny VGG 11 with 5 time step for NCARS. And we can see that even we did the test in ISO architectures, we sometimes have ISO accuracy or just a slight drop of accuracy. When we look to the energy analysis, we observe that for each network, the energy memory cost is predominant. And if we look into the details, we observe that for SNN, the memory cost is above the synaptic energy operation costs by several order of magnitude. But even with this result, we can see that we have 6 to 8 times more efficient solution with the SNN than the FNN. And we are far from the factor 100 of before in the literature. To conclude this, we see that we have seen that our energy estimation matrix is we've seen the energy estimation matrix here, so that allow a better comparison between formal neural networks and spiking neural networks with the energy and with the memory cost that is highly predominant. This work allows us to publish a paper for this conclusion, but we know that we did an approximation for the memory access, and we didn't take into account any memory optimization for the formal neural networks. But at the same time, in 2022, Dorfhofer and colleagues released papers that conclude in the same way as us. They found that the SNN activity must be below 40% and can be up to 7.3 times more energy efficient than FNN. In their works, they use memory access optimization for FNN, but their metrics, because of this comparison, it's harder to generalize. And also, for this work, in 2025, Dr. Thomas Louis offer a better SRAM cost approximation for quantized network that updates our metrics. And now that we have seen our energy estimation metrics, we can see the deployment tool that we've built. During my thesis, I contribute on the development of Qualia framework, which is an end-to-end open source framework that allows training, quantization, deployment, and evaluates of different neural networks, spiking and formal. It has 18 datasets available, uniform metrics, and can address microcontroller and CPU. This work is based on plugins, as you can see at the top. These plugins, for example, we have the SNN plugins that allow the support of spiking neural networks, of course. We also have the split plugin, which allow us to automatically configure the VHDL package of the split accelerator in order to deploy and evaluate spiking neural networks on FPGA directly. And each experiment of Qualia is described in a configuration YAML files in order to enroll the different functionality of the framework and have all the estimation of the network that we want. And to go a step further, we decide to facilitate the benchmarking of these results by produced by Qualia using Qualia Bench. Qualia Bench is an online platform to manage benchmark, analyze model, to manage and benchmark the analyzed model locally trained with Qualia. To this, we just need to send to the platform the configuration experiment files and the weight of our networks. We then, on the server, test the solution on CPU and on FPGA directly in order to reach all the metrics that we can have with Qualia. And then we can have access to performance, activity, operation count, energy estimation, latency, and resources utilization. And all this experiment can be set to public view, allowing public benchmark and with normalized, shared, and reproducible results. And this platform is online since June 2025. And with this, we've seen that SNN can be truly energy efficient in practice, and we release some tools to easily explore and deploy embedded SNN solutions, as we see before. So now we can search, now that we have all the tools and see that we can evaluate spiking our network approach, we can search for next features in our workflow. And we wanted to evaluate the scalability of our approach with complex event-based vision solutions. To do that, we we try to address embedded event-based object detection. This use case is just a use case when you need to classify an object in an image, as here. In order to compute the performance of this kind of application, we need to compute the intersection of a union, which is that we can compute here. This intersection of a union allows us to compute the true and false positive and the true and false negative. With this, we can compute the precision, which is the quality of the positive detection, and the recall, which is the completeness of the detection compared to the ground truth. And with this, we can compute the average precision that leads to the mean average precision in order to evaluate our network. So in 2022, Dr. Gordon released the state-of-the-art approach for event-based object detection with spiking neural networks. And he worked on the Gen 1 dataset, which is an event-based dataset with more than 2,000 samples of 60 seconds and can detect car and pedestrian. This dataset was labelized by hand with normal cameras at a frequency of 1 to 4 hertz. And for this work, Loic did the aggregation for the event frame on a 5 millisecond binary or accumulated event frame. Our goal here was to use one of these solutions in order to deploy it at scale on the FPGA board to see our limitation. And we choose the 32 spikes in VVV, which has more than 1 million parameters and offer 0.18 MAP. But we can't deploy it directly on the board because it was too big, so we had to reduce the channels of the bigger layers, which give us the small 32 spikes in VGG that have just around 1 million parameters and have just a little drop in MAP, which is going to 0.14 with a 32% of activity. And with this kind of network, we could, this network is a hybrid network, which means that you have spiking neural networks backbone and formal neural networks heads. With this experiment, we could test at scale the experiments with the limit of the board, but also hybrid deployments with spiking neural networks and formal neural networks on the board. Here is the network. So we can see to deploy the backbone and splits, we need to target 16-bit fixed points quantization of the weight, potential, and bias. We use the Qualia gen to generate the C codes and perform the simple post-training quantization. We observe that the network on CPU, we train it, we test it on the workstation CPU. The network has 150 milliseconds inference time, which is more than the 50-second accumulation at the beginning. So we know that we are not real time for this work for now. But we try to deploy it on the FPGA board, on the CPU of the board. But we pass from few hours of testing on the workstation to more than a week needed for the CPU on the FPGA board. So we just focus on one sample to do the test that we will see here. And we can see that on the CPU board, the inference time is around 1,800 milliseconds, and which is only 1,500 milliseconds for the backbone. Also, if you look at the power of the CPU of the board, which is 1.8 watts, we can compute the energy needed for this solution, which is 12.3 joule. And after this, we deploy our solution on splits. So we deploy the backbone, only this backbone in blue on splits, and we can see that with this, we have a 3.3 fold gain in energy, thanks to the 0.7 watts power needed by the backbone. But also we did an inference which is 2.2 faster, with 700 milliseconds of inference. And we have quantitative results in the image here, corresponding for each version of the network on the platform CPU floats, the quantized platform CPU, and the split results. But even with this interesting results, we expected less latency actually. In order to find why, we did a little, we just looked closer in the activity of the network. Here the results, sorry. And when we observe the latency, the layer-wise activity of a model, we observe the disparity between the layers. If we compare it with the number of spikes per layers, we observe that the layers with the biggest activity are not the one with the higher number of spikes. As the activity is normalized by the number of layers, we can see that the layer-wise activity or average activity is not really representative of the workloads. Instead, the number of spikes per output is more relevant, as we can see in blue here. This observation reveals a computational bottleneck with the first two layers that are circled in red, that have more than 4,000 spikes each, going to the saturation of the layer NPU. By curiosity, we pursue this analysis to reveal that even the channels has a disparity in activity. And with these elements, we can conclude here that we proposed the first embedded event-based object detection with spiking networks on neuromorphic hardware for the Gen 1 dataset, which allow us to publish these results. We highlight the importance of detailed sparsity and workload analysis to reveal the computational bottleneck possibility. We show almost 1 joule per output solution with 3.3 energy gain and 2.2 faster solution than the embedded CPU solutions. We now also see the at-scale limit of our hardware deployability capacity, and we can explore more complex architecture, but also ask some questions about these results, which ask ourselves if the disparity in the channels is an issue, or if can be if the channel sparsity disparity is an issue, or if we can take advantage of this information for efficient hardware processing. And now that we see this scalability needs, we can explore more complex architecture for future neuromorphic deployments. And to do so, we decided to address a more complex use case, which is the spacecraft pose estimation. Just to see for neuromorphic and space application, the first occurrence of embedded systems, embedded SNN accelerators for space application is the OPSAT mission in 2019, where the first version of Split was sent in orbit in order to do in-orbit processing of Earth observation images with spiking neural networks. In 2021, Roth and colleagues released a study to show that event-based cameras can be resilient to radiation environments, studying a single event effect on the event-based cameras, paving the way for space event-based vision application. In 2022, the TechEdSat 13 missions sent the first neuromorphic processor in space with an Intel OE1 processor. And the same year, in 2022, Mark Haag and colleagues sent to the ISS the Falcon Neuro mission, which stands for space-based observation of lightning using event-based sensors, and the study was published in 2024. And in 2023, Jawad and colleagues released the Scenic dataset. Scenic dataset is the first event-based dataset for spacecraft pose estimation. It is composed of synthetic data, and real event-based data. The synthetic events are generated from rendered RGB sequences, and the real event data were acquired on a robotic test bench and a 3D mock-up of Hubble. In this result, they have 22 unbalanced trajectory under varying light and speed conditions, as we can see on the top right here. And this trajectory, they have also like the different scene, and we can see also the number of ground truths and the time for each trajectory. And finally, even if it's the first event-based dataset, this dataset has some format issues between the synthetic and the event data. So in order to do some application in this dataset, we decided to only use even the real event-based data that were acquired on the test bench. To try pose estimation, we decided to try direct end-to-end pose estimation, which worked with a neural network that directly computes the rotation and position error vector. For pose estimation, a survey in 2023 of Polly and colleagues declared an acceptable zone for a solution which less than 20 million parameters, 30 centimeters of error, and 4 degrees of error, for rotational degree of error. And to see if we can fit in this range, we propose the small spiking end-to-end networks. These networks take as inputs binary features of 100 millisecond binary frame over one time step. He has two branches to output the translation and rotational prediction error. And for the last layers, we just removed the activation in order to have a floating point value rather than spike only. We trained 6 versions of this network with and without batch norm, and with a different scheduler for the spiking neural networks, step LR and cosine. And as the dataset is small and unbalanced, I decided to test my networks on three different sets of train and tests to do a 3K-fold analysis. And we can see here the average results on the 3K-fold analysis. We see that we have an interesting position error, but if we look in detail in this analysis with the min and max result for the 3 different K-fold that we choose, we can see that there is a variability. There is a nice variability between the min and the max, which can be representative, which means that it's difficult to form a representative train and test with a small and unbalanced amounts of seconds, even if we can see that our network is network converge. This little exploration allows us to publish this proof of concept in a Space 2024 conference, but it also offers us the opportunity to go further with indirect spacecraft pose estimation by joining the IRT Saint-Exupéry project, the Raptor project. In this project, they wanted to explore embedded AI solution for pose estimation with indirect approach, meaning that we need to use a network to compute the key point regression map on 26 points, and then feed a PNP solver to retrieve the translation and rotational errors. In order to do this application, they use the MoveNet architecture on the Raptor dataset, which is a grayscale images of 2048 image of the Sentinel-3 satellites that we can see in grayscale here. And my work consisted in assessing the feasibility of this spiking MoveNet, and it identified the technological barriers that need to be overcome in order to deploy these complex architectures on neuromorphic hardware such as SPID. Our network, this network is 1.9 billion parameters. Yes. To explore this limitation, let's see the backbone of the network. We have an encoder and decoder parts. So the encoder is leading to a bottleneck in the D4 block. And then we go to a decoder part, and there is also skip connection. So we have here the detail of the formal neural network version, which is mainly composed of convolution layer arrangements. And to build the SNN version, we need to do some adjustments, and in order to keep the binary sparse and event-driven behavior of this information transmission inside the network. The first observation is a warning. In this architecture, they use depth-wise convolution, composed with a group and point-wise convolution. And unfortunately, a lot of neuromorphic hardware doesn't support this kind of convolution. So that's why it's just a warning. We also need to add some activation in some part of the network in order to keep the spiking behavior. And we also see that there is some upsampling layers that are also not often supported by neuromorphic hardware. And finally, there is also the presence of a residual connection. This connection with aggregation nodes are also often not supported. We need to explore how to interpret or implement these kind of features on neuromorphic hardware in order to deploy this kind of network in the close future. We found that the upsampling with a nearest mode can be interpreted as a duplication of events on the hardware. And also we found that to use residual pass with addition, we can sum on all the events, even if we use binary frame interpretation. But you can sum at the software level, and in hardware level is interpreted as an event duplication at the beginning, and then as a successive processing in the next layers. I didn't have time to explain the detail of this study here, but this is the result that we've seen for this. But also, this kind of residual pass can lead to latency and memory access overhead that can impact the energy consumption of the network. So there is a warning on this part. And now that we have identified the limitation of the hardware deployment, we can also look at in the result of this kind of network and the activity analysis. For the results, looking at these exploration results, we see that our networks doesn't really perform well, but even the baseline with a post score over 1 isn't really sufficient at all to access the poorly acceptable zone. But we think that the main issue of this work was the input resolution of the network, which is really low compared to the 2048 resolution of the inputs. But even if the performance wasn't the targeted wasn't the target in this exploration, we can see a really interesting behavior of the network. We can see first the sum of the 26 key point heat map prediction, showing that our SNN can focus on the targets, as you can see on the right on the presentation. But also, if we look at the operation counter metrics, we can see that even with 5 time steps, our spiking neural network display 2.2 less operation than the formal neural network solution, with an average network activity in 26.68%. As previously done with the object detection, we also conduct a layer per layer activity analysis that also I didn't have time to present here, but we can resume the results in this array. We decide to display the minimum and maximum statistical activity over the test sets to evaluate the variability of the network activity. We also had a little study. We try to put all the input as 1 for the 5 time steps, and to see what happened in the activity in the network. these results show us that the activity inside the network didn't explode at all. These metrics offer a better view of the activity networks, and it's more realistic to, it's more easy to understand the behavior of the activity of the network. And it's also easy to implement. So we did this in order to show that we can easily do it, in order to see it more in the literature. With these results of this exploration, we can this conclude our last section, and also it concludes this speech. So, in conclusion, I can see that I contribute the elaboration of energy estimation metrics for a more realistic formal neural network and spiky neural network comparison. I also contribute to the SNN support in our framework, the Qualia framework, and also co-supervised and tests the tools and the workflow methodology toward the optimization benchmark of Qualia Bench. I published the first event-based object detection with spiky neural networks on neuromorphic hardware for the Gen1 dataset. I also proposed a proof of concepts with the first fully event-based spacecraft pose estimation with spiking neural network. And also we see different methods of sparsity analysis that can be interesting to generalize in the literature with the layer-wise and channel-wise analysis, the chain effect for residual connection aggregation, and the weight input analysis. Also, all the work that we've seen here had a co-design impact for the next version of the split architecture with the support of multi-NPU per layers, and also the residual and upsampling support that is now available, I think. And with this, we can see the future works. For the future works, I think that we need to continuously improve our framework and the benchmark also, but also encourage any benchmark initiative for better comparison, collaboration, and fair comparison in the literature. And I'm of course thinking about the NeuroBench initiative here. I also think that we need to investigate how to reduce the memory impact of spiking neural networks, even more when we are using residual connection. And in this way, just to see about what about graded spikes. I also see for space application that we are in needs of event-based datasets in order to build better space application. And also, I think that we have every element for event-based, embedded event-based vision payloads for spacecraft application. And so we can build it now. And we propose a project on this subject to the European Commission, I guess. Yes. And finally, in a more long-term vision, I think we can. This work can contribute to a hybrid platform with formal neural networks and spiky neural network accelerator, with optimized workload partition for very low power and embedded systems. And with these findings in the thesis, we had it allows us to impact the beginning of 2 theses on ANR projects that are beginning in this laboratory. Here is all the list of all my publication and the contribution, and that's the end of my presentation.
The jury has deliberated. Jonathan, you have made a clear and structured and didactic presentation of your work entitled Sparsity Optimization in Spiking Neural Networks for Embedded Event Vision Processing. This work is important, timely, and interdisciplinary at the intersection of hardware, design, and machine learning. You have clearly explained your contributions towards higher efficiency embedded AI, your experimental validation, and spatial applications that you targeted, such as object detection and pose estimation. The contributions span from theory to physical implementation, including the development tools Qualia and Qualia Bench. The jury particularly highlights the extent of your work. The presentation raised a large number of questions from an interdisciplinary jury, and you were able to successfully answer numerous and technical questions, and you engaged in interesting and in-depth discussion in this broad domain, demonstrating your scientific maturity and vision. The diversity of the questions and the breadth of discussion showed that you successfully acquired expertise in these domains of research. For all these reasons, the jury is unanimous in awarding you the title of Doctor of Université Côte d'Azur, specializing in electronics. Congratulations.
In the presence of my peers, with the completion of my doctorate in electronics, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principle of research and integrity. As I pursue my professional career, whatever I choose my chosen field, I pledge to the greatest of my ability to continue to maintain the integrity and my relationship to knowledge in my method and in my results. Thank you. So, I have a lot of people to thank, actually. I will, of course, I will start in English, but after I need to pass in French because some people didn't handle it. So first, I will really thank my reporter, Chiara and Timothée. Thank you for the time that you've taken to read my work and give a feedback. It was really interesting to read the feedback. So thank you so much for this time and also for the discussion. And I hope that we can continue to discuss after because I think we have a lot of things to discuss about. So thank you for your time. Also, thank you to all of you, to all the jury. Jean, to be the president of the jury, and all the Christian, and also you are not working far from here, so we often see you, and it's always a pleasure to see you and discuss about all these interesting topics. I will also wanted to thank Laurent. Thank you so much to come from the Netherlands, from the European Space Agency, to see this thesis. So it's a matter a lot for me. And it's always a pleasure to discuss with you, so I'm really happy to see you here. Vincent, I have a lot of thanks for you, because you keep your trust in me during my master degree. So thanks to you, you opened me the gates to space application with the test bench hobby that I love to work on, and you... I really think that you are a kind of person, when you work with this kind of person, you naturally give the best of you. And so I really want to thank you about this because I changed a lot since I worked with you. So thank you so much. And it's a real pleasure to see you here. I'm really happy to see you in these days. So thank you so much. And finally, Alain and Benoit, my thesis director. Alain, you... we didn't see us so much during the thesis, actually. But each time I was in need, you were here, always supportive, always smiling, and it was each time the good advice to move on. You did a really great job for the team, the H team, so it was really a pleasure to work in this team, thanks to you, and I'm really happy to have you in my side on this project, so thank you so much. And Benoit. Benoit, I have so many things for you. We discussed a bit yesterday, but yeah, we did the crazy adventure, actually. because when it starts, it was like different works, and we try to do everything that we see here today. And actually, I know 2% that when you work with, you want to give the best of you, and you are the second one that I know in my life. So thank you so much for that. And it was a real pleasure to work in the team. And as I said before, it was a really crazy adventure. We did so many things. We've seen the field evolve. We've seen so much things. It's at the end of this world, thanks to you, I have a PhD. I'm a doctor. I have comics. I pass on TV. I went to an ESA conference. I discussed with NASA guys. It was so many crazy things in this adventure. So thank you so much for all of this. And also, I have to thank you, thanks everyone here. I will switch in French. Sorry, Chiara. Donc, je voudrais tous vous remercier aujourd'hui d'être venus, d'être venus pour un peu voir tous ces travaux. Remercier le labo, donc le LEAT, pour toutes les personnes. On a la chance, ça je le dis aussi pour vous remercier, mais aussi pour les doctorants qui commencent, d'avoir un laboratoire qui est assez incroyable. C'est plus une famille qu'une équipe de travail. Il y a toujours quelqu'un pour venir vous aider, et émotionnellement ou dans le travail. Donc merci à toutes les personnes du laboratoire, sincèrement. J'ai forcément plus envie de remercier mon équipe, avec laquelle j'ai beaucoup travaillé. Et je te cherchais, PE, un énorme merci, parce que franchement, sans toi, on n'en serait pas là. J'ai appris tellement de choses grâce à toi, et tu as tellement apporté de choses à l'équipe. J'ai vraiment beaucoup de remerciements à te faire, donc un énorme merci pour toi. Et donc en plus de toutes les personnes du laboratoire, j'ai eu plein d'amis pendant cette période. Aussi la famille, il y a beaucoup de gens que je voudrais remercier. Je vois tout le monde ici, c'est assez incroyable. Il y a mon équipe de hockey aussi qui est présente, avec laquelle j'ai eu la chance pendant ma thèse de devenir champion de France avec vous. Donc merci à vous pour toutes ces choses incroyables qu'on a pu vivre. Merci bien sûr à tous mes amis qui m'ont supporté. Ça descend même de Rennes. Donc c'est incroyable. Merci beaucoup. Ma famille, bien sûr. Il y a ma maman qui est ici, avec mon beau-papa, Régis. Ma mamie, j'ai aussi en ligne mon papa et ma belle-mère avec mes frères et sœurs. Donc ça me fait super plaisir d'avoir tout le monde réuni aujourd'hui. J'ai une famille même un peu étendue parce que je considère aussi les Vadjini qui n'ont pas pu venir aujourd'hui, mais qui m'ont grandement aidé pendant mes études à grandir, mais aussi pour au final faire le podcast qui va venir après. Donc beaucoup de personnes à remercier. Merci à tout le monde, merci à toi Jeff, surtout d'être venu pour un peu encadrer tout ça, et qu'on ait un petit mémoire, une petite vidéo pour après. Donc merci beaucoup. Merci à tout le monde. Pour pas vous tenir plus longtemps, je peux vous inviter à un petit podcast qui va se préparer dans la cafétéria juste en bas du bâtiment. Donc encore merci à tous. Et...